I think we'll go to the next about integration, and that will be Kaushik Das from the DTU. Please go on, Kaushik. You are muted, Kaushik.
Yes, thank you. Now I'm unmuted and I'll share the screen.
Now it's on.
Okay, great. So I am Kaushik Das. I am from DTU Wind Energy. I'm a researcher here. And this presentation is about integration of distributed wind in the power system. And so we have broken it into two parts. One looking from the DSO, the system operator's perspective, and another one is more for off-grid, mini-grid system, island system, smaller system, which Tom will talk towards the end of the presentation. And the definition of distributed wind, which Anka was showing before, what we came up in IEA task 41, is not only the small or medium wind turbines, rather not focusing on the size, but rather on the distributed application. And then that has been defined as normally up to 70 kV, where it is connected to the distribution network. So and that can be even larger wind turbines. In Denmark, we have seen even 3 megawatt wind turbines and up to 5 wind turbines with a plant controller, like a 15 megawatt wind farm also connected there. But that only makes it interesting and more challenging, I would say, to have all these different scope of the turbines connected to the grid. Some of them are in front of the meter, some of them are behind meters, whereas some of them are very small kilowatt scale, whereas many of them are much more controllable and observable at a megawatt scale. But why is this more challenging for integration is that if you look at this very famous picture from the EnergyNet, although it's a bit old, that from 1990 to 2014, how Denmark has evolved in terms of the generation, and then moving from very centralized plant to very distributed generations, and many of these distributed generations are wind turbines, as you can see. So that brings up a very many new kinds of challenges. And when we started dividing up the challenges, I tried to break it up a little bit in terms of who do we look the challenges from, like from systems operators perspective, that this gives a newer kind of challenges, that suddenly the more and more generations have started flowing from the household or lower voltage levels to the transmission systems. As a result, and this is a global problem, maybe not so much problem in Denmark, because the Danish distribution systems are generally a bit more robust and stronger than many other countries, I would say. But that have started increasing more and more losses in the system. Also, the voltage profile management becomes a bit difficult for them. And then this new concept of not so new but still a bit evolving concept of TSO DSO coordination has been coming up, where the flow between the TSO and DSO, mainly the reactive power flow, has to be controlled in order to not create problems into the transmission system as well. But then if we look at them as challenges, they are challenges, but this can also start up some new market opportunities for the smaller wind turbines connected in the distribution network. And that's the angle when we look from the distributed wind turbine manufacturers perspective. And that's what Tony was mentioning before, that stricter requirements from distributed wind turbines have been included in the grid code, be it frequency support or volt var control and harmonics. I mean, they are also required for now type B wind turbines as well. But also newer system support capabilities have been evolving in terms of the technology. So grid forming capabilities, black start, load following, all these new technologies have been coming up. and then they might come up in at a later stage also in the grid codes, and mainly for off-grid and islanded systems where distributed wind play even bigger role as compared to a large power system like European or Danish power system, where we have many big wind turbines and bigger offshore wind farms taking some of those roles as well. At the same time, we have this evolving global markets. The wind turbines are being placed into further deserts in Mongolia or in Bangladesh or in Kenya or South Africa. And Tom is gonna talk about his challenges in working in Kenya. And many of these are connected to the weaker grids, and then advanced control or operational strategies need to be developed for for controlling the wind turbines, but also not only from the grid perspective, but also from the wind turbines point of view, because if most of them gets disconnected for a long period of the time because of the grid being weak, then that also hampers the business in general for these smaller winds or distributed wind turbines. At the same time, there are evolving technologies such as hybrid systems, more towards like for with storage and solar, um, and in the off-grid systems or smaller systems or island systems, which is becoming more and more relevant. Also because due to the reducing cost of solar PV and storage, and then we can use some of the negative correlations between wind and solar, that the both of them don't peak up at the same time. So that is a very good mix. So I think there is a general notion of saying that wind is against the solar or vice versa, but then in hybrid system they can really play along. So now I'll talk of so DTU Wind Energy has been working in multiple projects over many years, and Anka was presenting a list before. Then I'll take one of the recent projects cases, and that might also answer Peggy's question, what we did for one of the distribution system operators in Jutland. So the project was called NetWind, which finished in end of 2018, and so this was kind of a demonstration project where we wanted to use the capabilities of wind power plants connected in the distribution network in order to better for higher performance of the distribution network. So from the DSO's point of view, so what we wanted to check was how much loss can be minimized in the network, you only using the wind turbines as controllable devices, the knobs there, but also how to maximize the wind power plant production during the maintenance of the grid. That many times the grid is under maintenance, and then they have to disconnect the wind turbines completely, losing quite a lot of production in the system, which is not good for the power system, neither for the society. So how it worked was, is it not? Yeah, we have it anyway. Is it still visible? The slides?
Yes.
Yes, great. So what we did is that we developed some algorithms in DTU Wind Energy, which we have put in the DTU Wind Energy cluster or the infrastructure, and then the distribution system operator INI would collect the data from the wind power plants, and then they would send it to us, DTU Wind Energy, and then we'll run those optimization methods here. And after that, we'll send the set points back to the wind power plants, and then they would send then there is a this is integrated into their SCADA, and then they would send to the wind power plant SCADA to control the wind turbines, and this is the loop. And unfortunately, the last link could not be established due to some practical challenges, but the rest of the links were established and tested. So somehow we could not complete the whole loop, but the framework was built. And we have the interest in additive wind energy to keep continuing this platform bigger and in more detail in future as well. So what was the optimization? It was mainly the reactive power set points of the wind turbines which we were controlling, and then we were minimizing the active losses in the 60 kilovolt network. And there were a couple of network constraints and wind power plant constraints, but we were also checking that this is something the grid code asks to have the capabilities, but the wind turbines generally have much bigger capabilities. So what is the benefit of using bigger capabilities of the wind turbine as opposed to the what only the grid code is asking, which is generally a bit a subset of the capability of the wind turbines. But then we did the loss minimization and we found out that around is 160 megawatt hour of losses could be optimized in the whole network over a whole year, which is not much in many sense, but also it is quite substantial if you look at the point that there is nothing more no more instrumentation or anything required in order to obtain this. So this gets accumulated over the years, and more if you have more networks, it only adds to your revenue from the distribution system operator. And then the next step would be to see that how this revenue can be transferred to the distributed wind turbines or wind power plants which are being controlled in order to remunerate them as well. So that we have not done in this project, but that's something interesting aspect we can look into it as well. But when we started looking beyond the project, then what we saw that it is not only the wind power plants which can help, but there are other tap changers in the on-load tap changes in the network which can also be useful. And then the capability curve, using capability curve gives a bit better capability to minimize those losses as compared to the only the grid code. But then another thing is that the big transformer which the distribution system connects to the transmission system, that plays a major role there. And this can be a good point of negotiation between the distribution system operator and transmission system operator, that you will let us allow us to control that transformer. That would help us minimizing quite a bit of losses inside our network. But at the same time, we promise to control the reactive power flow to your network. And that's the right figure we have there, that losses and the reactive power play against each other. So if you try to control one of the knob, then the other gets relaxed. So then you have to find out a weight that you should not be pushing too much reactive power into the network in order to minimize your losses. But then we extend this study beyond the 60 kilovolt to lower voltages, and we have a ongoing PhD project within the Marie Curie project, WinGrid, where we continue this research, where we also use our capability to do weather modeling and weather forecasts into the distribution network, so to find out how more better we can control the smaller wind turbines, which are generally not observable to the distribution system operators as well. Whatever is below 10 kilovolt or 400 volt, the distribution system operator does not have a real information there. So then I'll hand it over to Tom.